You've seen the headlines, right? AI that can whip up incredible art or write code in the blink of an eye. But here's the thing. The AI that does all that amazing stuff is usually way, way too big for the phone in your pocket. So how in the world do we shrink these digital giants down to size without making them, well, dumber? Let's get into it.
It all comes down to a fundamental mismatch. I mean, a huge one. On one hand, you've got these super powerful, massive AI models running on servers in the cloud. And on the other, you've got the slick little device you're probably holding right now. The gap between them is the whole problem.
And to really get a sense of the scale here, look at this number. A top-tier AI model today can have around 7 billion parameters. You can think of each parameter as a little knob the AI twists as it learns, getting smarter with every single turn. Now get this. Back in 2012, a leading model had just 62 million. That is an absolutely explosive growth in complexity. All that complexity creates a very real-world headache. That huge cloud AI might need 350 gigabytes of memory just to run. Your phone? It probably has around 4 gigs. That's not just a gap, it's a canyon. It's like trying to park a cruise ship in a bathtub. It's just not going to work. So how do we solve this? How do we shrink that cruise ship down to the size of a toy boat but keep the engine? Well, this is where a really clever set of techniques comes into play. It's called model compression, and it's the key to making powerful AI work right there in your hand. So, how does this digital magic act actually work? We're going to break down the 3 main ways engineers put these giant AIs on a diet. They're called pruning, quantization, and knowledge distillation. Let's dive into the first one.
First up, we have network pruning. And honestly, the best way to picture this is to think of a sculptor trimming a bonsai tree. You start with this big, overgrown, complex network, and then you carefully snip away all the connections, all those parameters that aren't really doing much, the ones that are redundant or just don't add value.
And the process itself is actually pretty logical. You start with the big, fully trained AI. Then you go in and algorithmically identify and just remove the least important bits. But here's the crucial final step. You give that new, leaner model a little bit of extra training, a fine-tuning, to make sure it's just as sharp as it was before the haircut.
And does it work? Oh yeah, the results are seriously impressive. A clever technique called lottery ticket pruning can strip out over 85% of a model's connections, which makes it way, way smaller, while it still holds on to over 95% of its original smarts. That's a huge win.
Okay, technique number 2 is network quantization. Now, if pruning is about removing parts of the model, quantization is about making the parts that are left a lot lighter. Think of it like taking a huge, high-resolution photo and saving it as a much smaller JPEG. You're simplifying the information without losing the main picture. So what's actually happening here? Well, these big AI models love to use really, really precise numbers with lots of decimal points. We call them 32-bit floats. Quantization just swaps those out for simple whole numbers, or 8-bit integers. It's a subtle change in the language the AI speaks, but it leads to way faster calculations and big savings on memory.
And the payoff is dramatic. Just switching to those simpler 8-bit numbers can cut memory usage by 75% and make the model's thinking process, what we call inference, more than 3 times faster. And if you get even more aggressive and go down to 4-bit numbers, you're looking at a nearly 6x speed boost. That's a massive gain in pure efficiency.
All right, our third and final technique is probably the most elegant of them all, knowledge distillation. The concept here is just beautiful. You take a massive, genius-level AI, the teacher, and you use it to train a much smaller, nimbler student model.
And here's the fascinating part. The student doesn't just copy the teacher's answers. No, it learns to mimic the teacher's entire thought process. It learns how the teacher gets to the answer, not just what the answer is. And this allows that tiny student model to soak up a huge amount of wisdom and pack it into a much, much smaller frame.
And the results here, they are absolutely staggering. Using an advanced version of this called progressive distillation, you can slash a model's size by over 97%. That's right, almost 100 times smaller. And at the same time, you can make it think over 11 times faster. This is how you get truly powerful AI into truly tiny spaces. And this isn't some niche experimental idea, you know. Knowledge distillation is quickly becoming the go-to method for researchers. And why is that? Because instead of just cutting things out, it actually transfers the nuance, the wisdom of how a big model thinks. That leads to smarter, more capable small models. In fact, its use shot up by over 31% in just 1 year. That tells you where the smart money is going. Okay, so we've seen the how, now for the really important part, the so what. How do these incredible shrinking techniques actually pop up in the gadgets and services that we use every single day?
Well, the short answer is pretty much everywhere. That smart speaker that gets your answer in a snap, the camera on your phone that makes every photo look perfect, the voice commands in your car, all of those rely on these compressed, on-device AI models to be fast, private, and super efficient. And the impact you can actually feel. Because of model compression, your smart speaker can respond almost 80% faster because it's not waiting on the cloud. A smart security camera can use nearly 94% less internet bandwidth. And your in-car voice assistant can hit almost perfect accuracy, even when you're driving through a tunnel with no signal.
We've covered a ton of ground, but believe me, this technology is really just getting warmed up. So where is all this headed? Well, it turns out the future is going to be incredibly small and incredibly smart. The real game changer, the next big leap, is going to come from putting all these techniques together. Just imagine it. First, you use knowledge distillation to create a brilliant little student model. Then, you prune it to trim off any excess fat. And finally, you quantize it to make it lightning fast. It's this multi-layered approach that's going to let us build hyper-efficient AI for everything.
And that really leads to a huge question about what's next for us. Because as these techniques get better and better, AI is going to move out of the cloud and into the very fabric of our world. So you have to ask, what becomes possible when it's not just our phones, but when every single device around us can think for itself?